Bismillahirrahmanirrahim and Assalamu alaikum. This is Faryal Javed, rule number 21 TE07 from Telecommunication Engineering Department, UD Texila. So today I am going to solve lab analysis 9 of digital signal processing, that is FIR filter using window method. So starting with the task 1 of today's lab, that require a book of Lee Tan, and its part A is from example 7.4, plot the filter in time domain along with its magnitude response. And here is the example that shows the filter coefficients h of 0. And then the part B is use windowing, that is Hamming, Hanning and Blackman with filters and observe their magnitude response. Discuss the window's magnitude response and note use n is equals to 512. So moving with the very first MATLAB code of today's task, that is the use of filter coefficients. And here we basically use a stem to plot the filter impulse response against the sample indices, that is n from -3 to 3 in time domain. This stem plot visually represent the amplitude value of the filter over discrete time samples. And then moving towards the magnitude response calculations and the plottings. So it basically use the FFT, that is fast Fourier transform of filter coefficients with a higher number of points, that is n is equal to 1024. This generate a more detailed representation of filter frequency responses. And here we use a frequency axis. F is defined from -pi to pi, corresponding to -0.5 into 2 pi to 0.5 into 2 pi, which represent the normalized digital frequency ranges. And the top subplot display the filter impulse response H plot against the sample indices and time domain. The bottom subplot shows the magnitude response of filter in the frequency domain with f on the x-axis and y on the y-axis. The frequency axis is limited from -pi to pi radian for the clarity and frequency representation. Moving towards the task first part B, that is the use of Hamming, Hanning and Blackman to give filter coefficients and plotting their magnitude responses. As we know that the Hamming window offers a good trade-off between main lobe width and the side lobe attenuation. It provides reasonable side lobe suppression, which can also reduce leakage effects in spectral analysis. Moving towards the Hanning window, the Hanning is similar to Hamming but offers improved side lobe suppression at the cost of slightly wider main lobe. Then the Blackman window provides the highest side lobe attenuation among these three windows but has a wider main lobe compared to Hamming and Hanning window. It is useful in application required in dynamic range excellent side lobe suppressions. So in this lab, we plot the magnitude responses, which shows the different window functions affect the filter performances, highlighting the trade-off between main lobe width and the side lobe attenuations. Moving to our task 2 of today's lab, that is plot the signal in time and frequency domain along with its magnitude response. F of s is equals to 8000, and then the x1, x2, x3, x4, and then the sum of these values. And the part B is to implement example 7.5, 17.10 for the given signal. So the MATLAB code of this task is this. So this code applies a Hamming window to give a filter coefficient age, and then convolve this window filters with the input signal using convolution function. The resulting, yeah, the magnitude response of the filtering signal highlights the frequency component affected by the filtering process, and it basically demonstrating the filter frequency selective behavior. Now the next task is the applications of FIR filters, and the first one is noise reduction. Implement example in section 7.4. Here is the section 7.4 that shows the application of noise reduction and a two-band digital crossover. And then the part B is for a given speech signal, discard required frequencies as a given in example, observe result. Then the part C is for a given music file, apply high and low pass filter to observe results, that is tweeter and woofer. Moving towards the part A of this task, that is noise reduction. Basically, FIR filter are versatile and widely used in various applications, that offering precise control over signal frequencies characteristic with straightforward implementation through convolution operation. Now the task third, and the part A is. So this MATLAB code implement an FIR, that is finite impulse response. Yes, that is the finite impulse response filter for a noise reduction. Here we have defined the array H, and these coefficients represent the impulse responses of FIR filters. Then we will generate the signal as an original signal is given by X comprising sinusoid components at different frequencies created, and Gaussian noise is added to this signal to generate a noisy version. Then we did the filtering process, that is convolution function is used to apply the FIR filter to noisy signal, resulting in a filtered signal that aims to reduce the noise present in that input. In summary, this code basically demonstrates the application of FIR filter to enhance signal quality by attenuating noise from noisy input signals, showcasing the fundamental use of FIR filter for noise reduction in practical signal process scenarios. And then we had the part B, that is for a given speech signal, discard required frequencies as given in example and observe result. Now the output to part B is. So in this task, the yes, and here is the output to this task. In this task, the speech signal is loaded from an audio file using the audio read. So a frequency axis is defined based on the length of FFT and the sampling rate FFS. This axis represents the frequency range from minus f of s over 2 to f of s over 2 in hertz. And then we have discarded the high frequencies, that is above 4 kilohertz are discarded by setting the corresponding indices in the FFT output x to 0. So the filtered signal is reconstructed in the time domain by taking the inverse Fourier transform. The I50 shift function is used to obtain this. So the original speech signal and the filtered speech signal are played sequentially using sound, allowing for the auditory comparison between original and processed signal. Overall, this code demonstrates how to analyze the frequency content of a speech signal using FFT, perform spectral filtering by discarding high frequencies, and visualize the spectra of the original and the filtered signal. The audio playback enables listening to the effect of filtering process and on the speech signal. Moving towards the other task, that is for a given music file, apply high and low pass filter to observe results, that is tweeter and woofer. So this MATLAB code applies a high pass and low pass buffer worth filter to an audio signal. The high pass filter attenuates frequencies below 500 Hz, while the low pass filter attenuates frequencies above 10,000 Hz. The original music signal and both filtered version are plotted and played back sequentially to demonstrate the effect of filtering process on the audio signal. Adjusting to the filter parameters and plot limits can be made for specific audio processing needs. Here is the original signal, and then we have the high pass filtered music, and then the low pass filtered music. So this is it for today's lab. Thank you so much. Allah Hafiz.